Yes, yeah, you can meet the speaker later. So our next talk is Alireza Marandi, and he's a professor of electrical engineering and applied physics at Caltech. He studies photonic integration circuits, and the title of his talk is The Meeting of Light and Intelligence.
Okay. Good evening, everyone. I'm really excited to tell you tonight a little bit about the hardware side of AI, particularly photonics, and hopefully I'll give you a flavor of the role of photonics in AI, and also how AI can play a role to build next-generation photonic technologies. So I put this graph here to remind everyone of why we're able to do the things we're able to do today. And that's mostly about the compute power that we have access to. So this graph shows you the number of floating operations that you need for training different neural networks as a function of time in the past 80 years or so. And you can see, of course, we love to use exponential fit, that we used to have only 40% growth per year, and then all of a sudden it turned into 4 times every year. Despite that, we still want to do more, and we're really operating at the edge of the hardware we have access to. So this is an estimate of how much it takes to just run the inference machine for ChatGPT. It doesn't include anything about the actual price of the machine or how much it takes to train, and those numbers are much larger than numbers you're seeing. And when you ask the question of why can't we do more, there are a few things on the hardware side that are limiting us. One of them is the Moore's law getting to its limit. Depending on which flavor or which variant or which descendant of Moore's law you believe in, it has either stopped or it's going to stop soon, because it's really hard to imagine that we can pack more and more transistors in the same chip size. But the other thing that has happened more recently is what we call the memory bottleneck. And the bottom line is most of the energy we're really spending in the hardware is spent not on the computation, but on the communication. So how you take bits from one place to the other is really limiting the power consumption of the hardware we have today. There are different ways of thinking about it, but this is one graph showing what happened in the past 5 or 6 years, which is if you think about the computation and the number of computation components you do, and you compare it with the memory, in the past 6 years, we are now getting to the point that the limit for how and what we can do is the memory. And that tells you that we're dealing really with the communication challenge. So the computing has advanced much faster than how we move the data around. And it has sparked a lot of hardware research in terms of thinking about some exotic or some slightly unconventional computing architectures, in terms of not thinking about having a processor one place and a memory in the other place and dealing with this bottleneck, bringing the memory closer to the computation, or in-memory compute is a direction that is really focused on substantially. And the other piece is how we can do the communication more efficiently. That's where photonics shines. Photonics has been the well-known tool for communication. If you think about a coaxial cable versus an optical fiber, you can imagine that how much more information you can transmit per unit time on the optical fiber compared to the coaxial cable. You can also imagine how much you don't need to spend much energy on the optical fiber because you don't have the loss of a coaxial cable. This has been proven. We have been doing optical communication starting from telecom back in 90s. So most of the backbone of the telecom system is built on optical communication. And the optical communication is moving its way deeper and deeper into our computing systems. So maybe in the past 15 years or so, we got pretty much all the data centers using optical communication, mostly rack-to-rack communications. Nowadays, the main focus is on board-to-board. How can we do even faster in the smaller scale communications? And it's moving deeper and deeper into chip-to-chip and even on-chip optical communication. But long story short, photonics for the communication task and addressing some of these challenges we have with the communication and all these big computing hardware is a direction that has been happening, and it's going to keep growing. And most of the challenges that we're facing are now engineering challenges in terms of how we can build the lasers into our systems, how we can build the modulators, and so on and so forth. And there's a lot of efforts in industry and academia to address this challenge. But if you think about the actual computing, there is a slightly different story. And if you want to think about the speed of computation in terms of the clock rate, this graph is showing how the clock rate of the CPUs evolved in the past maybe 30 or so years. And you can see that there was an exponential growth early on, but then it got kind of to this ceiling, which is about 3 gigahertz. So 20 years ago, if you bought a computer, it was a 3 gigahertz or 2.6 gigahertz clock rate. Today, it's probably close to 3. So that's not a fundamental problem, but that's also tied to the energy consumption. So there's really not much we can do to get the electronic processors to go faster than 3 gigahertz for the clock rate. And one of the hopes is that maybe photonics can help here as well, not just for the communication, but also for the computation. Can we actually use photonics to do computation? And that's where photonics doesn't do well, and at least yet. So one of the problems with photons is that if you pass two laser pointers, they don't really talk to each other. And that's not what happens with electrons. That's why in semiconductor physics, we can build these transistors, which are nonlinear. But in photonics, it's really hard to get that kind of functionality that light controls light, unless it passes through what we call a nonlinear material. One example is lithium niobate. But we have had maybe more than 2 or 3 decades of integrated photonics, just similar to electronics, but way behind electronics in terms of the size of these circuits. But most of the photonic integrated circuits that we have been building on are linear. So you might want to consider electronics without transistors. So all the components are really resistors, capacitors, inductors type. So it is still not completely useless for computation. We can still do linear operations, such as matrix multiplication. And that's one of the directions that people are going after. Can we just use a photonic processor as an accelerator for all the AI hardware we have? Typically, the challenge is that we need to do optical to electronic and electronic to optical conversion, and that's usually a showstopper. But despite that, people are still pushing this direction. But if you really want to make photonics compute, you really need to make nonlinear photonics. And almost any meaningful computing system you think about, including neural networks, you have the nonlinearity in them. If you want to think about the electronics, of course, the big example is how we did switching, starting from vacuum tubes, and then we got into transistors, and then integrated transistors, and that led to the digital revolution and that graph that I showed you early on. One of the questions that we are really thinking about hard is how we can utilize the similar kind of functionalities in photonics. And if you look at photonics, we're probably 50 years behind electronics. So we are talking about probably the time between the radio transistors in 1950s and integrated electronics in 70s in the photonics world. And that's one of the directions that my group is heavily focused on. How can we build these nanophotonic circuits and these devices that can build based on the functionality of something like transistor. So I'm going to show you only one example to just give you a flavor of what are the kind of functionalities we get and put it in perspective for computing. And I'm going to show you an all-optical switching example. So this is a very simple photonic device. It's just a waveguide. I'm not going to go into the details. I'll just tell you that the cross-section of that waveguide is submicron, so it's really nano. I will not tell you the length yet. But with that, we can actually replicate the very famous ReLU function, just that function, as the main nonlinear function that we need to build, for instance, neural networks. And I'm going to show you this comparison plot to see how it behaves. And what I'm showing is on the x-axis, we have the energy per activation. On the y-axis, we have the time it takes to get that activation function to work. And of course, you want to be in that corner, so you want to have a fast, low-energy activation function. This is where current CMOS technology fits. So this is an estimation. So if somebody actually has done the device, don't complain. We actually just looked at the whole value and estimated that. But you can see that it's in the order of a few gigahertz again. That's the clock rate that we're limited in. And the energy it consumes. This is where things were with most of the optical experiments. That's the weakly nonlinear world we were living in photonics. And this is the kind of work we have been able to do with the technology that we have been building on, which is based on lithium niobate nanophotonics. So when you look at that data point, again, I remind you, this is only the ReLU function. You can see that it is a few orders of magnitude faster compared to the electronics. The energy is not yet there. But what I didn't tell you is that this device is 6 orders of magnitude longer than a transistor. So in terms of the size, we are nowhere to compete with transistors. We can compete on the speed. And the big question is now, how can we really utilize that speed to be able to build some computing functions that can be meaningful and helpful for all the computing needs we have? So the first thing is, if you can do it with volume of transistors we have access to, if there's an architecture that is built on billions of transistors, like what you have in the palm of your hand, then we should not compete. So the volume game is really not the game for photonics. So it's always about the speed and thinking about the architectures that are not easy to implement in the electronics hardware. So we have been working on a few of these architectures. So this is an example of a cellular automata. So I'm not going to tell you too much about how we implement that, but that's one example of a computing architecture which is not a good fit for electronics hardware. We can do simulation of that in electronics hardware, but it's a perfect fit for optics. And we have shown some preliminary results on that. We have also been building on just looking at hard optimization problems and how we can map them directly to the optical hardware so that we can surpass the idea of just simulating them using standard electronics. And we have also been looking at reservoir computing and recurrent neural networks. So these are the kind of architectures that we know are better fit for optical hardware. And we have been able to recently show that the clock rate story that I told you, that we are limited about a few gigahertz, we can break it with these architectures and get to the 100 gigahertz range. Now, what I didn't tell you, and I'm kind of happy I'm not showing you the results tonight, is what kind of problems we actually solved. And that's kind of embarrassing for this audience because these are relatively, well, these are very small problems that we look at in this hardware. So then the question becomes, what are the potential benefits we can get with these ultra-fast systems that can compute, but it can't really be so big? And we focus on the computing problems that need super low latency. So one example is that memory wall that I talked about. So there's a lot of room for some simple compute going into the memory infrastructure of the hardware platforms that we're dealing with today. But there's also a lot of other potential applications. You heard from some of the physics potential applications that really require low latency computation. But what I also didn't tell you is that those limitations we have on photonics makes the design of the circuits really hard. So this is not simple building blocks like the logic gates and the transistors that we can build architectures and circuits on those. This is more like open-ended, nonlinear responsive devices. And we need to think about how we can utilize some sort of smart ideas to be able to design circuits. This has been a focus of photonics maybe in the past 10 years or so. So people have been looking at just doing inverse design, utilizing the standard electromagnetic solvers, mostly for linear components. More recently, there has been transitions to replace those electromagnetic solvers with neural networks. So now we can have much faster response time because of the trained neural network. And it also makes the inverse design much better. But these are all linear, so we're not super interested in those. If we go to the nonlinear circuits, then things become a lot more open and a lot harder. So this is an example of the work we have been pursuing with Anima's group. So we're trying to simplify some of the meaningful potential functionalities of the nonlinear circuits. So in this case, we have been looking at how we can start with a long pulse, take it in the picosecond range, and get to the very short pulse in the femtosecond range. And that would be useful for many different applications. We still haven't been able to pull out something that would work substantially well, but we can try things that we can't think of because the system level design is so hard and so complex. We can let the AI tool think about what kind of device configurations and circuit configurations they can pull together. So we're excited about this direction because it's hard and because we also have access to these tools and would not only enable us to think about some building blocks such as just pulse compression, but also thinking about sensing and computing type applications that can benefit from some relatively complex photonic circuits. So with that, I'm just gonna show you the summary. Hopefully I gave you a flavor of how photonics have been an important building block of the hardware for AI. Hopefully I gave you some sense of how AI can help building the next generation of photonic devices. And I have here my group. This is actually in the same Huntington garden. And with that, I stop here and thank you for your attention.